Good morning, everyone. Welcome to today's presentation. I'm excited to share with you the topic of semaphore in operating system. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. In this session, we will explore the fundamentals of semaphores, their role in managing processes, and how they help in synchronization within an operating system. Let's get started. Let's begin with an introduction to semaphores. A semaphore is essentially a synchronization tool that helps us manage access to shared resources in a system where multiple processes are running concurrently. Think of it as a traffic light or a signaling mechanism that ensures only the right number of processes can access a resource at a given time. This is crucial because without proper control, you can run into race conditions, where multiple processes try to modify shared data simultaneously, leading to inconsistent or incorrect results. Semaphores help prevent this by enforcing mutual exclusion, meaning only one process can access the critical section at a time when necessary. The concept was proposed by Edsger Dijkstra back in 1965, and since then, it has become fundamental for process synchronization and inter-process communication, or IPC. Overall, semaphores are vital for maintaining order and correctness in complex concurrent systems. A semaphore is essentially an integer variable that we use to manage synchronization between processes. It acts as a signaling mechanism to control access to shared resources. The key thing to remember is that a semaphore is only accessible through two specific atomic operations: wait, also known as the P operation, and signal, which is sometimes called the V operation. These operations are crucial because they guarantee that no two processes can modify the semaphore at the same time, preventing race conditions. This atomicity is what makes semaphores powerful tools in ensuring proper coordination and avoiding conflicts in concurrent systems. So, in the broader context of process synchronization, semaphores help us maintain order and consistency when multiple processes are competing for resources. Let's take a closer look at the different types of semaphores. First up, we have the binary semaphore, also known as a mutex. Its value can only be either 0 or 1, which makes it perfect for ensuring mutual exclusion. That means it helps us control access to a single resource, so only one process can use it at a time, preventing conflicts or data corruption. Moving on to the second type, we have the counting semaphore. Unlike the binary version, this one can take on any non-negative integer value. It's especially useful when we have multiple instances of a resource available. For example, if we have several identical printers, a counting semaphore can help coordinate access among multiple processes efficiently. Both of these semaphore types are crucial tools in our overall goal of managing concurrent processes safely and effectively. Understanding their differences and applications helps us design better synchronization mechanisms in our systems. Let's take a closer look at semaphore operations. First, we have the wait operation, often written as wait, S. When this is invoked, it essentially decreases the value of S by 1, so S becomes S minus 1. Now, here's the key part. If after this operation S becomes less than 0, that means the process has to wait or get blocked. It's like saying, there's no resource available right now, so the process has to pause until it can proceed. Next, we have the signal operation, or signal S. This one increases S by 1, so S becomes S plus 1. And if after this increment S is less than or equal to 0, that indicates there's at least one process waiting for the resource. So in that case, one of the waiting processes is resumed or unblocked. An important point to remember is that these operations are atomic. That means they happen as indivisible steps, preventing race conditions. This atomicity ensures that multiple processes don't interfere with each other when modifying the semaphore, maintaining consistency and synchronization. Overall, these semaphore operations form the core mechanism for controlling access to shared resources, helping us avoid conflicts and ensuring orderly process execution. Let's take a look at how a semaphore works in practice. First, we initialize the semaphore variable to the number of available resources. This setup helps us keep track of how many resources are free at any given time. When a process wants to access a shared resource, it performs a wait operation. Think of wait as a way of saying, I'm about to use a resource, so please check if it's available. If the resource is available, the process proceeds. If not, it waits until it becomes free. Once the process is done with the resource and leaves the critical section, it calls signal to release it. This action essentially increments the semaphore, signaling that the resource is now available for others. The key idea here is that this mechanism ensures that only a limited number of processes can access the shared resource simultaneously, which helps prevent conflicts and maintain data integrity. Overall, this process of initializing, waiting, and signaling forms the backbone of resource management in concurrent systems, making sure everything runs smoothly and efficiently. Let's take a closer look at this example of a semaphore used for mutual exclusion. Here, we initialize the semaphore mutex with a value of 1, which indicates that the resource is available. When process P1 wants to enter the critical section, it performs a wait operation on the mutex. This reduces the semaphore value to 0, effectively locking it and preventing other processes from entering the critical section at the same time. Inside the critical section, P1 can safely perform its tasks. Once it's done, P1 signals the mutex, increasing its value back to 1, which allows other processes to proceed. The same sequence applies to process P2. This mechanism ensures that only one process can be in the critical section at any given moment, maintaining mutual exclusion. This example highlights the core idea of using semaphores to coordinate access to shared resources, which is fundamental to managing concurrent processes effectively. Let's take a closer look at this semaphore example, which illustrates the producer-consumer problem. In this scenario, the producer adds items to a buffer, while the consumer removes them, and they need to coordinate to avoid conflicts. Semaphores come into play here with 3 key ones. Empty, which keeps track of how many empty slots are available. Full, which counts how many filled slots there are. And mutex, which ensures that only one process accesses the buffer at a time. These semaphores work together to prevent the buffer from overflowing, meaning more items being added than it can hold, or underflowing, where items are removed from an empty buffer. By carefully managing these semaphores, we maintain synchronization and keep the producer and consumer working smoothly without conflicts. This example highlights how semaphores are essential tools for managing concurrent processes and ensuring system stability. Let's talk about some key advantages of using semaphores. First, they enable efficient process synchronization, which means they help coordinate the activities of different processes smoothly without wasting resources. This is crucial in multitasking environments where processes need to work together seamlessly. Second, semaphores play a vital role in preventing race conditions. Race conditions occur when multiple processes access shared resources simultaneously, leading to unpredictable results. Semaphores help control access and ensure that only one process manipulates shared data at a time, maintaining data integrity. Next, they are a simple yet powerful mechanism for resource management. Despite their straightforward concept, semaphores provide a robust way to allocate and deallocate resources, avoiding conflicts and deadlocks in the system. Finally, semaphores are versatile and applicable to many classic synchronization problems. Whether it's producer-consumer, readers-writers, or other well-known scenarios, they provide a common, effective tool to manage synchronization challenges. Overall, the advantages of semaphores highlight their importance in building reliable, efficient, and synchronized systems. Let's talk about some of the disadvantages of semaphores. First, they can be quite complex to implement correctly. This isn't just about writing code, but ensuring that the semaphore logic works perfectly in all scenarios. If not done properly, it can lead to serious issues. One major problem is deadlocks, which happen if semaphores are used improperly. Imagine a situation where two processes are waiting on each other to release resources. It can cause the system to hang indefinitely. Debugging these synchronization issues can also be quite difficult. When things go wrong, pinpointing the exact cause isn't always straightforward, making troubleshooting a real challenge. Lastly, semaphores lack an ownership concept. This means that misuse or misunderstanding of how they should be used can lead to indefinite blocking, where a process is stuck waiting forever. So, while semaphores are powerful tools for managing concurrency, it's important to be aware of these potential pitfalls and use them carefully within the broader context of synchronization strategies. Now, let's talk about deadlock and starvation in semaphores. Deadlock happens when two or more processes are stuck waiting for resources that the other processes are holding, and nobody can move forward. It's like a standstill where each process is waiting for the other to release something, and that wait never ends. On the other hand, starvation occurs when a process gets stuck waiting indefinitely because the scheduling algorithm favors other processes, often unfairly. This means some processes might never get a chance to run if the system keeps prioritizing others. The good news is that by using proper semaphore techniques and smart scheduling algorithms, we can prevent both deadlock and starvation. These tools help ensure resources are allocated fairly and efficiently, keeping our system running smoothly. So, understanding these issues and applying the right strategies is key to managing concurrent processes effectively. Let's wrap up with a quick summary of semaphore. Semaphores are a type of synchronization primitive, and they play a crucial role in managing resource sharing in concurrent systems. Think of them as signals or flags that help control access to shared resources, ensuring everything runs smoothly without conflicts. There are two main types of semaphores: binary semaphores, which are like simple on-off switches, and counting semaphores, which keep track of multiple resources. Both types use two fundamental operations: wait and signal. The wait operation is used to request access, and the signal operation releases it. Semaphores are powerful because they help prevent race conditions, those tricky situations where multiple processes try to access shared data simultaneously, leading to inconsistencies. However, while they are essential tools, they require careful implementation. If not handled properly, they can lead to deadlocks, where processes get stuck waiting for each other indefinitely. So, in the context of our overall theme, understanding how to effectively use semaphores is key to designing safe and efficient concurrent systems.